Hello, my name is Sudhir Krishnan and I am Director of Wireline NFV Product Line Management. Today we will be showing a demonstration of Casa Systems vBNG control plane and data plane redundancy solution. Casa's vBNG disaggregated solution offers geo-separation of control and data planes. The solution includes redundancy that will automatically detect and recover service following an unexpected hardware, network, or software failure event on the control plane or on one of the data plane instances. Control plane redundancy is provided using an active standby model with the standby instance running on a different server than the active one. In case of any failure on the primary control plane, the standby takes over all the sessions, including routing and IP addressing without service impact. The data planes continue to function during the switchover from primary to standby control plane. Data plane redundancy is provided using a N+1 model. In this model, a service instance of vBNG data plane resides in a chosen disaster recovery location as a backup for n BNG data plane instances. When a BNG data plane failure or loss of data transmission is detected, the sessions are moved to the backup BNG data plane without subscriber service disruption. Once the primary BNG data plane is repaired and online, then a revert can be automatically initiated to move subscribers back to the primary. This is also done without service disruption. BNG data plane redundancy is orchestrated by the control plane, which holds state on all data plane instances. Let's take a look at the demonstration.
Thanks, Sudhir. So before we deep dive into the demonstration setup and the actual demonstration, let's first review the goal for this demo. The goal for this demo is to display the vBNG high availability and resiliency functionality in action that allows the subscriber session to stay intact and online, and the subscriber traffic forwarding to continue uninterrupted when the messaging interface framework between the active control plane and the active data plane is disconnected, that prompts a DP switchover. The active data plane will perform the redundancy switch to the standby data plane when the inter-CP DP communication channel is down. So the sequence would be as follows. The management and the inter-channels between the CP and the DP are all in up status. The subscribers are online and bidirectional traffic is sent. Then we disconnect the control channel between the CP and DP and verify the DP switchover is activated. The expected result is that the subscriber session will stay online successfully and there will be no significant traffic loss between the data plane and while the switchover happens. The subscriber session is still online without redial, and we can observe from the CLI that the user sessions have switched over to the standby data plane, which is now the active data plane. Now that we have talked about the goal for this demonstration, let's now move on and take a deeper look into the demonstration setup. So as you can see here, this is the vBNG control plane and data plane redundancy demo architecture. There are two vBNG software control planes. One is active and one is standby. The CPs are running on x86 server using OpenStack. So you can see from here these are the control planes that we were talking about. We then have two vBNG software data planes, each running on KVM on separate x86 servers. So as you can see here, these are the data planes that we're talking about. Out-of-band management access is available to all the CPs and all the DPs. The radius that is used here for this demonstration is a free radius that is running as a separate VNF. The inter-CP DP control channel traffic is being passed via a top-of-rack switch. So the control channel traffic between the CP and the DP is going via this top of rack switch, as you can see here. The connection to the radius server and to the management PC or the lab PC, as you can see from the diagram, is via a top of rack switch. Talking about this. The data plane subscriber traffic ports are connected to a top of rack switch, which is in turn connected to a Spire and Test Center port for subscriber traffic simulation. So this is the portion that we just talked about. So the data plane ports are connected to the top of rack switch, which is the same top of rack switch where the control plane, data plane, control channel traffic is flowing, and it is in turn connected to a Spire and Test Center. So we have the core and access ports from the Spire and Test Center connected to a top of rack switch, and we have distinguished them by VLANs. Now let's take a look at the CLI, the BNG CLI. We can run some commands and take a look at how the setup is currently. So you can see here the hostname dp-ha_demo is the BNG CLI. So if you run a show system, you can see here there is 4 nodes in total. Node 0 and node 1 are the control planes, and node 5 and node 6 are the data planes. Node 1 is the master control plane and node 0 is the slave control plane. Node 6 is the running data plane and node 5 is the standby data plane. So let's first start with the DP-HA demonstration. So as you can see here, the DP5 is the designated standby node and DP6 is the active node. You can also see all the CPs and DPs are running now. The HA configuration that we are going to demonstrate today is a 1+1 CP-HA and an N+1 DP-HA. And for N, today what we have is 1. The active HA that we have here is 1. So it will be a 1+1 DP-HA as well. Now let's do one thing. Let's now go to the Spire and Test Center and bring up a subscriber session online. So this is a Spire and Test Center. Port 2/8 is the core port and 2/7 is the access port. So let's bring up a IPOE subscriber online. So we can see an IPO subscriber is bound. So now let's go to the CLI to check on that. So if you run a show subscriber, or you can see that the subscriber is online. Now let's pass some traffic bidirectionally. So we go to the stream blocks and run both downstream and upstream traffic. So from the detailed stream results tab, you can see that there is counters increasing on both the downstream and upstream direction. We can take a look at the advanced sequencing tab, where you can see the frame counts increasing on both the directions, and on the dropped count and dropped frame count, or dropped frame percent count tab, you can see there is no increment there. It's basically zero there. So you can see there is no activity in the dropped count column, which means there's no packet loss currently. Let's go to the CLI and type in a command. So we are currently sending upstream and downstream traffic of 10 Mbps each, and you can see using the command from a subscriber level, from a per subscriber level, you can see that we are getting that speed, 10 Mbps on both directions. There is no drop because the policy associated to it is for 10 Gbps. We can also take a look at the total throughput on the server level using this command. So you can see here both sides, we can see an aggregate throughput of 20 Mbps each. So on both the access and the core side. Now, the next step is to trigger a DP HA scenario. So basically what we will do is we will disrupt the control channel port on the active DP, which will initiate a DP switchover. So just to remind you, the active DP is node 6. So let's go to node 6 and disrupt the control channel port on node 6. So as you can see, this is the server where the DPs are running, the active DP and the standby DP. When we run a wish list, you can see the VMs running. Now let's bring the node on, or the control port on the active DP down. So this is the network that carries the control channel traffic. So we will be bringing that down. So that network has been brought down. Now, if we go back to the CLI of the vBNG and run a show system, you can see that the active node 6, which was active earlier, is not ready, in a not ready state, and node 5 is the running node right now. So node 5 has taken the active role of the DP. Now let's go back to the Spirent test center and take a look at the detailed stream results. So as you can see here, the traffic is still flowing on both the upstream and downstream direction, and you can see there is no activity in the drop counts yet, even though a DP switchover has happened. You can also see the details of the HA trigger from the show HA log command. So the show HA log would give you the details of what type of HA failure happened and which node took the active role and which node took the standby role, and what are the details related to this particular trigger. So you can see here the last activity that happened is here, which says software fail is a type. The reason was the subtype for it was no keep alives. So the failed slot was DP6 and the take slot was DP5. And there's a little bit more of a detailed information on that regard, which says no SIG message from the active CP. So when we brought down the control port on the DP, it kind of like disrupted the sync message being communicated between the active CP and active DP, which triggered the switchover. If you look at the show subscriber all output, you can still see the subscriber is in its earlier state. There is no need for a redial. It is still in its earlier state, so that is good. Next, we can recover the DP6 connection by bringing the DP control port to up state. So let's go back to the DP server where the active and standby DPs are running. So let's bring back the control channel. So with this command, we will bring back the Casa _int network back up. So we have brought it up. Now we can go back to the vBNG CLI and run a show system command. So you can see here the node 6 has now recovered. It was in a not ready state earlier and now it is in the DP config state, which means it is rebooting. So you can see slowly it will transition to the standby state. So we have a HA command called HA revert time. So basically what it does is it is the time for the DP to revert back to its original state. So DP6 was originally the active DP. And if you look at the HA config that we have issued here, the revert time configured is 3 minutes, which means that once the DP6 is back online and in standby state, it will reprise its earlier active role in 3 minutes. So let's wait for the DP6 to be in standby. So right now the node 6 is back in the standby state. Now let's wait for around 3 minutes past this current uptime for it to reprise its original state, which is the running state or active state. On this parent test sender, you can still see traffic forwarding happening. There is no drop count here, so you can still see that. On the show HA log, you can see the log messages for HA related triggers, both the data plane type as well as for the control plane type. This is the server where both the data planes are running. So we just need to give it a minute or so, and then you can see node 6 becomes the active node and node 5 becomes the standby node. You can see subscriber stats, real-time traffic flowing through the subscriber, 10 meg up and 10 meg down. So as you can see, now the node 6 is back into its original role, which is the active DP role. And as you can see, node 5 has now rebooted. Now it will come back and reclaim its original state or original role, which was the standby node. So you can see that while this happens, you can still see that there is traffic flowing without any issues. There is a small, insignificant frame drop, and you can still see the subscriber maintaining its state, and there is no need for a redial. So right now the node 5 is in DP config state. Very soon it will get back into the standby role. You can also see the information in this regard from the DPHA log message, which says it's of type switch back. And the reason was the auto revert back command that we gave for 3 minutes. And it was a system level switchover. Yeah, so now you can see that the node 5 is in standby state. So that's about it with regard to the DPHA. Now on the control plane, we have a 1+1 HA model. So how we can demonstrate here is to manually reboot the active control plane and see how the standby control plane takes over the active row. So as you can see from here, the node 0 is the standby CP and node 1 is the active CP. Let's run a manual command, which is a manual HA command that will protect the active CP by triggering the standby CP to take the active role. In the meantime, the active CP will reboot. So let's take a look at that. So the command is HA node. Then we have to give the node ID, which is 1 for the active node, 1 protect. So once we entered that, we don't have access to the CLI because the active CP is from where I am running the CLI. So it kind of immediately reboots. But I have already set up a SSH session with the standby CP. So let's log into that. So you can see here, I have logged into the standby CP, which is now active. So you can see here, the earlier active CP says, this is the slave CP. Please log in to the system from the master CP. So this is the one above is the master CP. So when we do a show system, you can see that node 0 is now the master node and node 1 is rebooting, and it will soon be the standby node. So now the node 1 is the slave CP. It is in standby state. You can see the HA logs in regard to this standby and active CP also from the show HA logs command. Type is manual because I manually switched it over, and it's for CP. So that's about it for DP and CP related HA configuration and demonstration. That's all I intended to demonstrate for this session. Thanks for viewing.
This demo has shown the vBNG control plane and data plane redundancy in action. Casa's Axiom vBNG is the only TR459 CUPS ready Tier 1 NFV solution that is available for deployment. Built from ground up as a cloud-native solution for both OpenStack and container-based cloud networks, Casa's Axiom vBNG easily addresses the greater diversity of broadband demands through a unique design that disaggregates network functions, streamlines packet flows, enables independent and dynamic scaling of control and data planes, and ultimately delivers superior throughput, accommodating both large and distributed capacity deployments. If you would like to go through a more detailed demonstration or would like more information, please contact your Casa salesperson or contact us at www.casasystems.com. Thank you.